So, we are going to learn about regression, its historical origin and its importance. The term regression has its historical origin, which is connected to the works of Francis Galton. While studying the height of parents and children, Galton found the following result, that tall parents usually have tall children and short parents usually have short children. But the average or mean height of children born of both parents tend to move towards the average or mean height in the population as a whole. In other words, the height of children of both tall and short parents tends to move towards the average or mean height of the population. The same concept was later on confirmed by the findings of Galton by analyzing thousands of records of height of both children and parents by Carl Pearson, and he confirmed this finding. So, the question therefore is, what is regression analysis all about? Regression analysis is basically a statistical tool or a method that is very useful for studying the relationship between any two or more variables and mainly, let us say, economic variables. For example, in economics, we have Keynes' theory of psychological law of consumption, which states that when income increases, there is an associated increase in consumption. However, I am sure we all know that the marginal propensity to consume would always lie between 0 and 1. There are other such examples of relationship between variables in social sciences. In such cases, regression analysis can be employed to build a model to predict the value of one variable, which is generally known as a dependent variable, on the basis of other given variables known as the independent variables. We therefore briefly explain this notion and the terminology used commonly in regression analysis. The most important notation is of a dependent variable, which is generally denoted by y, and then we have independent variables generally denoted by x1, x2, x3, x4, and it can extend up to xn, where n is the number of independent variables to that particular relationship. The terminology which we mainly use is of dependent variable. Also, they are known as by other different names such as explained variable, predicand, regressant, response, endogenous variable, outcome, or controlled variable in some experiments. Similarly, independent variables are also known by different names or different terminologies. They are also known as predictor, regressor, stimulus, exogenous variable, covariate, control variable, and so on. Though the use of terminology is a personal choice, we will simply use dependent and independent or explanatory variables in this particular lesson. So, first of all, let us try to understand the distinction between deterministic and stochastic or statistical relationships. In regression analysis, we look for a statistical relationship and not deterministic relationship between variables. In a statistical relationship, we essentially deal with stochastic or random variables that possess probability distributions. For example, the yield of crop depends on temperature, rainfall, fertilizers, but agronomists could not predict the yield of crop exactly because there are errors involved in measuring these explanatory variables, and there are other factors affecting crop yield. Therefore, in a statistical relationship, you will find that the dependent variable and explanatory variable does not have always an exact relationship. Whereas in deterministic relationship, the relationship between variables can be exactly determined. One such example is the Newton's law of gravity. According to Newton's law of gravity, the force of attraction between every particle in the universe is directly proportional to the product of the masses, and it's inversely proportional to the square of the distance between them. There are other such examples as in Ohm's law or Boyle's gas law. Let us now therefore understand the difference between regression versus causation. A statistical relationship between two or more variables does not in any manner imply causation. For instance, we know that crop yield depends on rainfall. Statistically speaking, there is no valid reason why we cannot assume that rainfall depends on crop yield. However, simple common sense suggests that this is not usually the case, as we cannot change rainfall by increasing or decreasing crop yield. Therefore, the crop yield is treated as a dependent variable and rainfall as an explanatory variable. However, simple common sense suggests that this is not usually the case, as we cannot change rainfall by increasing or decreasing crop yield. Therefore, the crop yield is treated as dependent variable and rainfall as explanatory variable. To determine causality between variables, we must take into account a priori or theoretical considerations. A statistical relationship in itself is not at all sufficient to imply causation between variables. What is regression and what is correlation? So, let us understand regression versus correlation. Both correlation and regression are closely related but conceptually different. In correlation analysis, our main objective is to measure the strength or degree of linear association between variables, that is between dependent or any two variables, between dependent or independent or even between other variables. For example, we are interested in measuring the correlation coefficient between smoking and lung cancer. In regression analysis, we are interested in predicting the average or mean value of one variable, that is the dependent variable, on the basis of the given values of other variables which we define as independent variables. For instance, we would want to know the occurrence of AIDS among drug users. Secondly, in correlation analysis, both the variables are treated as random. However, in regression analysis, the dependent variable is a random variable while the explanatory variable is fixed and given. Once we understand the difference between regression and correlation, let us try to know what is data and especially the economic data. The success of any regression analysis will depend on the availability of high quality data necessary for economic research. So, we briefly look at the types of data and issue of data accuracy. What are the types of data? Generally, there are three types of data available for empirical analysis, which are known as time series data, cross-section data, and pooled data, which is nothing but a combination of time series and cross-section data. In time series data, we measure the set of observations at different time periods, which could be daily, which could be monthly, which could be quarterly. We have very many examples of such kind of data. For example, stock prices, weather reports are examples of daily data. For weekly data, we have like money supply, we have weekly sales. Similarly, for monthly data, we have consumer price index, we have unemployment rate. For quarterly data, we have and we may have GDP, industrial production, etc. Similarly, for annual data, we have government budgets and we may extend it and we may have quinquennially data which is measured over 5 years, which is census of manufacturing, and decennial data which is census of population, which is measured every 10 years. The problem with time series econometrics is that we need to assume that the underlying time series data is stationary, which we would explain later on. But simply speaking, it means a time series data is said to be stationary if its mean and variance remain constant over a period of time. Let us now try to understand the cross-section data. In cross-section data, we measure the data on one or more variables at the same point in time for different people or different sections. Examples are census of population after every 10 years, consumer expenditure survey, etc. The problem with cross-sectional data relates to the issue of heterogeneity. So, when we include heterogeneous units in a statistical analysis, the size and scale effect needs to be considered into account. So, cross-section data is basically data at a point of time across sections. Pooled data is a combination of both the time series and cross-sectional data. For example, we can have a data on the price and output of different varieties of clothes for a time period of say 10 years, which could be sales of different firms over 10 years period producing or same commodities. The issue of data accuracy is very important in all these types of data. There are a lot of data available for empirical research in economics. However, the quality of data is often not very good. There are very many reasons for that. First reason is that most data in social sciences are non-experimental in nature. Therefore, observational error due to omission or commission may creep in during data collection. Now, measurement errors may also arise due to approximations and rounding off in experimental data. Rounding off basically means that you may round off to nearest decimal points or maybe to 2, 3, 4 decimal points, which is generally done in most of these experimental kind of a data. Then we also have the problem of non-response, and it is very much rampant in questionnaire type surveys, where very many people are not willing to respond to the questions which are being asked to them by different surveyors. It is also often difficult to compare various sample data as there are wide differences in the method of obtaining data between these surveys, or maybe between over the period. There may be changes in some of the questions, or some of the objects of response may also change. It is also possible sometimes that economic data are available in highly aggregated form, which means at a very macro level, and it may not contain much information about micro units, which means for individuals. Therefore, it is possible that if the quality of data is poor, it may lead to unsatisfactory results for the economic researchers. And researchers have to be very careful in using these kind of data and coming to some conclusions or results on the basis of such data. Having understood the types of data and the importance of good quality of data, let us now try to understand what are the different types of regression model. Generally, there are usually two types of regression models which we use. The first is the simple regression model, which may be further divided into simple linear regression model and simple non-linear regression model. Similarly, we may have multiple regression model. Now this can also be further subdivided into multiple linear regression model and multiple non-linear regression model. So in a way we have a four-way classification regression model divided into simple and multiple, and each one of them further divided into linear and non-linear regression models. In simple regression model, the number of independent variable is 1, while in multiple regression model it is more than 1. The term linearity also has different meanings. It could mean both linearity in parameter or linearity in variables. For regression analysis, linear regression model would mean a model which is linear in parameter but could be non-linear or linear in terms of the explanatory variables, but it has to be linear in the coefficients. The non-linear regression model would mean a model which is not linear in parameter. So by linearity in parameter, we mean that the parameters, say B0, B1 has the power 1 and are not multiplied or divided by any other parameters like B0, B1, or which is B0 into B1 or B0 upon B1. So in a way we have a classification which is linear in parameters or non-linear in parameters, and linear in variable and non-linear in variable. Therefore, there are four possibilities: a model which could be linear in both parameter as well as variable, a model which could be non-linear in variable but linear in parameter, is still known as linear regression model, and similarly we may have a model which is linear in variable but non-linear in parameter and is known as non-linear regression model. And the last category could be which is non-linear in both variable and parameter and comes under the category of non-linear regression model. We can have different examples of these models such that linear regression model could be expressed as y is equal to beta 0 plus beta 1 x, which is a simple linear regression model, or we could also write down y is equal to beta 0 plus beta 1 x square. This is also an example of simple linear regression model. However, x power is 2, but the power of beta 0 and beta 1 is exactly same and is equal to 1, and therefore we still call them as a simple linear regression model. So the third possible kind of an equation could be where y is equal to beta 0 plus beta 1 x plus beta 2 x square. Now this is an example of multiple linear regression model because we have more than one explanatory model variable, in this case x and x square. So it is a quadratic equation. And then we can also have y is equal to beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cube. Now this is also an example of a linear regression model but is known as a cubic regression model. But if I also express y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, then also we can have an example of a multiple linear regression model, and the power of all the parameters in this case is equal to 1. The last example could be of a non-linear regression model where we can express dependent variable y equal to beta 0 plus beta 1 square x. Now this is an example of simple non-linear regression model. But if we write y is equal to beta 0 plus beta 1 square x1 plus beta 2 cube x2, then this would be an extension and would be known as multiple non-linear regression model. Having understood these different type of models or the distinction between, let's say, a linear regression model and a non-linear regression model, let us move further and try to understand what is a population regression model. Now in regression analysis you will find that our main aim is to estimate and or predict the population average mean value of the dependent variable based on the known values of the explanatory variables. We consider in our table 1, you will find that an illustrative example of the weekly income X and of weekly expenditure on consumption of a hypothetical community. The total population comprised of 36 families. These families are further divided into 6 income groups from rupees 1000 to rupees 3500. We have 6 fixed values of X and the corresponding Y values are shown in the table. So we have 6Y subpopulation. The bottom row shows the conditional expected value of Y for the 6Y subpopulation. So let us look at this table 1, which is an illustrative example of weekly income and weekly expenditure on consumption. I am sure you can very well notice that we have in the columns the income and the consumption, and this X value is given as 1000, 1500, 2000, 2500, 3000, 3500, which are the weekly income of the households, and their corresponding consumptions are given in the cell values with each column, and which are known as weekly consumption, which is our dependent variable or the variable in which we are interested. And if you look at the total, then we have these total as the total weekly consumption of all the households with that particular level of income, say for example 1000 to 3500. But if you look at the last row, then in the last row we have the expected value of consumption given a particular level of mainly income. So if you look at this number 800, it gives you the mean consumption of all those households whose weekly income is rupees 1000. Similarly, 1100 gives you the mean consumption, mean weekly consumption of all those households whose weekly income is 1500, and so on. So this is what we can see from the last row, which is very important kind of an information which one can obtain from this table. So we can find this conditional probability also for this population of 36 observations from the same table. Now this can be seen in our next table, which is table 2, which gives us the conditional probability for population of observations of these 36 families. Now again we have income on the front side, which you can see in our rows, and in our columns we have the conditional probability of Y given Xi. So if you look at the cell value 1 by 5, what we are saying is that it is the probability of a particular level of consumption given a particular level of income. So if the income is 1000 rupees, we are saying probability is 1 by 5 that this particular household or particular family will have a particular level of consumption. Similarly, because there are only 5 families in this category. Similarly, if you look at the next level of income, which is 1500, since there are 6 families, therefore the conditional probability of each of these families is 1 by 6, and so on. You can similarly notice the conditional probabilities for other income levels, and the conditional means are also given, which are same as was given in our previous table, which is 800, 1100, 1400, 1700, 2000 and 2300. So these conditional means basically it implies in a way that given a particular level of income, how much would be the mean consumption of these families. So 2300 basically implies that families whose income is 3500 would on an average have the weekly consumption of 2300 rupees. Now we can plot the graph of this relationship between expenditure on consumption and income in our figure, and this is what is being done in figure 1. From this we can clearly see that there is enough variation in expenditure on consumption in each income group. However, the average expenditure on consumption rises as income rises. This phenomena can be seen in table 1 itself, where for example we see that when income level is rupees 1000, the corresponding expenditure on consumption is only 800. But when the income is increased to 1500, the average expenditure on consumption rises to 1100, which is 1100. Thus, we clearly see a positive relationship between income and expenditure on consumption. Now, these mean or average values of dependent variable, which is consumption expenditure, are known as conditional expected values, as they are conditioned or depend on the given explanatory variable, which is income group in our example. Now, apart from conditional expected values, we can also find unconditional expected values of expenditure on consumption, which can be denoted as EY. Now, how do we find it out? We add the expenditure on consumption of all income groups and divide it by the total number of families, which is 36 in this case, and this comes out to be rupees 1583.33. Now, it is unconditional as it includes expenditure on consumption of all income groups, and the conditional expected values are different from the unconditional expected value. The unconditional expected value gives the average expenditure on consumption of all income groups, while the conditional expected value gives the average expenditure of consumption of a particular income group. So, I am sure you would understand this distinction between conditional expected value and unconditional expected value. And conditional expected values are different for different income groups. That is what we have already explained to you. Now, let us look at the objective to obtain this population regression line, because that is what is the essence of entire regression analysis. The population regression line is obtained by joining the conditional mean values of y for various levels of x, which means we are joining the conditional expected mean values. Now, geometrically, the population regression line is the locus of conditional means of dependent variable for given values of the explanatory variables. The regression curve thus passes through these conditional mean values. We assume for simplicity that these y values are symmetrically distributed around their respective conditional mean values. Now, this can be seen in figure 1, which is before you, where you can see that how for each level of weekly income, which is 1000, 1500, 2000, etc., we have these mean weekly consumption expenditure denoted by 800, 1100 and 1400, and we also have the distribution of these consumptions given a particular level of income denoted by these curves. So, this is what basically the diagram is trying to show it to you. Let us now try to understand the population regression function. Now, we know what is a population line, but how do we represent it into a regression function? So, continuing with the above example, the example which we have discussed just now about income and expenditure, we have seen that how conditional mean of expenditure on consumption depends on particular income level. Therefore, the expected value of y given a value of x, which is in this case, as we have already said, income for a particular value which is xt, is a function of xt, where xt is given value of x. So, mathematically we can write that expected value of y given xt is equal to the function f of xt, which is our equation 1. So in this equation 1, we have function f(xt) which denotes some function of the independent variable x, which means we are only saying that expected value depends upon some function of x, but what is that function? That exact functional form we can write down depending upon our assumptions and what kind of a model we want and what is this functional relationship exactly. So this equation 1 is also known as a conditional expectation function, which we can in abbreviated form write CEF, or also known as population regression function. Now this function tells us how the expected value of the distribution of y is related functionally to the value of xt in some way. Therefore, the question which arises is that how do we relate this functional form, which is fx? What shape or what form is it going to take? So the functional form of the population regression function is both an empirical as well as a theoretical question, and we have to answer this question. Therefore, for instance, many economists assume that expenditure on consumption and income are linearly related. For simplicity's sake and as initial working hypothesis, we assume that the population regression function, which is the expected value of y given xt, is a linear function of xt. Hence, we can write down this function as E expected value of y given xt is equal to beta 0 plus beta 1 xt, and this is or this can be defined as equation 2. So in this equation 2, beta 0 and beta 1 are known as regression coefficients. The regression coefficients are fixed but unknown, and beta 0 is known as intercept or constant term, and beta 1 is known as the slope coefficients. Equation 2 is also known as linear population regression model, and our main objective is to find out the true values of beta 0 and beta 1, and also to find out the standard error of beta 0 and beta 1. Let us now try to understand the specification, which can also be known as stochastic specification of the population regression function. Now, coming back to our example, we find that the average expenditure on consumption increases as income increases. I am sure you are very clear now on this. But if you look at a particular family, this need not necessarily be true. For instance, there is a family with income of rupees 1,500 whose expenditure on consumption is just rupees 850, which is below the expenditure of one family whose income is rupees 1,000. So therefore, we are trying to say that there are families whose consumption expenditure deviates from the average expenditure, and this deviation of individual yt from its expected or mean value can be expressed, and it can be seen that it could be both positive as well as negative. So we write this deviation as mu t and is equal to yt minus expected value of y given xt. Similarly, yt is equal to expected value of y given xt plus mu t. Now this is our equation 3, and we have another equation which is that yt is equal to beta 0 plus beta 1 xt plus mu t, which is equation 4, which we have obtained by substituting the value of expected value of y given xt. The deviation of this yt from its expected value is, in this case you can see, denoted by the mu t. Now mu t is an unobservable random variable and can take either positive or negative values. They are popularly known as stochastic disturbance term. Let us now interpret this equation, which is our equation 4. The equation says that the expenditure on consumption of an individual family for a given income level can be expressed as the sum of two components. The first component is the systematic or deterministic component, which is represented by expected value of y given xt, which is nothing but the average expenditure on consumption of all the families with the same income level. The second component is the random component or non-systematic component, which is represented by the stochastic disturbance term mu t. Now, to understand the issues more clearly, we write the hypothetical example in our table 1 in the form of equation 3. The individual consumption expenditure for x equal to 1000 can be written as y1 is equal to 700 is equal to beta 0 plus beta 1 into 1000 plus mu 1. Similarly, we can write down the value of y2 equal to 750 is equal to beta 0 plus beta 1 into 1000 plus mu t, and so on. Now, all these values therefore can be written as a function of beta 0 plus beta 1 into the income level 1000 plus some kind of a random value. Now, how do we find out these random values? This we would also like to understand. So, the conditional mean of this disturbance term is to be obtained, and this can be written as in equation 3 we take expected value of both the sides and we obtain expected value of yt given xt equal to expected value y given xt plus expected value of mu t given xt. Now, this we have written for a given level of income. Now, the right hand side is reduced to equal to expected value of y given xt plus expected value of mu t given xt, because expected value of a constant is the constant itself, and therefore, there is no change in the first term. Now, since we know that yt upon xt is equivalent to expected value of y upon xt, we get expected value of mu t given xt equal to 0 from the right hand side. So, what we are trying to say is that the left hand side which is equal to expected value of yt upon xt is equal to the first term on the right hand side. Now, the stochastic specification in equation 3 therefore clearly shows that there are other variables apart from income which affects expenditure on consumption, and income alone cannot explain individual family consumption expenditure. Let us now try to understand the role and importance of the stochastic disturbance term mu t. This disturbance term mu t captures all omitted variables that collectively affects or may affect y, the dependent variable, but are not included in the model. The question is why it is not possible to introduce all the terms that affect the dependent variable explicitly into the model. There are many reasons for this. Now, there is always some element of intrinsic randomness in human responses. This arises due to unpredictability of human choices, errors in making decisions, among others. An effect of large number of omitted variables is contained in X. Due to incompleteness of theory or data unavailability, there are large number of explanatory variables which are excluded from the model. There could also be error in measuring the dependent variable. Then we also know that the functional form of the function fx is not always known. In reality, it is very difficult to know the exact functional form of the relationship between dependent variable and independent variable. So our objective is to estimate population regression function, which is known as PRF, from this entire relationship. In reality, we cannot observe or see the population relationship between the dependent variable y and the explanatory variable x. So we use sample information to estimate population values. Now consider two random samples drawn from our population, which was represented in table 1. These two random samples could be that we have sample 1 where we take the values of y as 700, 915, 3050, 1800, 2150 and 2400, which is given in your first column, and the corresponding values of x are given in the second column, which ranges from 1000 to 3500, which are the income levels. The second sample consists of again the expenditure denoted by y and income denoted by x. The income levels are same, 1000 to 3500, which means we have kept income as fixed, but the values of expenditure, which is y, is now different and it ranges from 800 to 2250. The sample regression function SRF is the counterpart of PRF, which is population regression function, and it can be expressed as SRF equal to yt hat is equal to B0 plus B1 xt, where yt hat is an estimator of expected value of yt given xt, and B0 is an estimator of beta 0 and B1 is an estimator of beta 1 of the population regression function. Now we draw sample regression curve or line based on this table 3, and this can be seen from the figure which is before you. Once you look at this figure, you will recall that the stochastic population regression function can be written as yt is equal to beta 0 plus beta 1 xt plus mu t, whereas the sample regression function now is written as yt is equal to b0 plus b1 xt plus now epsilon t. So instead of mu t, we are now using a new notation et, and let me explain and make it very clear that mu t and et are not exactly same, but yt hat is the conditional expected value or predicted value of yt. So et, which is now used, is the deviation, or which is also known as the residual or error between predicted value of yt hat and the actual value yt. Therefore, we are saying that mu t is not equal to et, but et is the difference between yt hat and actual yt. The main objective of regression analysis is to estimate the population regression function with the help of the sample regression function. The sample estimates will be used as an approximate of the population parameters. These sample estimates will also vary from one sample to another sample. So our task will be to estimate that sample regression function which make this approximation as close as possible, because in that case SRF can be satisfactorily used in place of the population regression function. Having said all this, let us now try to summarize what we have learned, because we must take a stock of what we have been saying in our last 45 minutes. And the main, I am sure you would agree, the main idea we have learned behind any regression analysis is to study the statistical dependence of dependent variable y on one or more explanatory variables x. The objective of regression analysis, we have understood, is to estimate and or predict the mean value of the dependent variable on the basis of the known value of the explanatory variables. We have also learned that the success of any regression analysis will depend upon the availability of high quality data. We have also tried to make it very clear that regression models could be of two types. They could be simple regression model or they could be multiple regression model. However, in both cases, we could have linear and non-linear regression models also. We have also studied that linear population regression function regressions are linear in parameters only. They could be non-linear in the explanatory variables. The population regression function or the conditional expectation function, which is denoted as CEF, remains the key concept behind regression analysis. We study how the average value of dependent variable changes with the given value of the explanatory variables. We have also learned that how the stochastic PRF, as they are useful for empirical analysis, and the stochastic disturbance term mu t plays an important role in estimating the population regression function. The learning also has been that the stochastic disturbance term mu t captures all the factors that influence the dependent variable but are not explicitly incorporated in the model. In reality, one rarely has the access to the entire population of interest. So we use the stochastic sample regression function to estimate the population regression function. Thank you, students. Thank you for learning all this.